Okay, so this video is going to be about linear regression. Basically with regression we want to talk about variables that are predicting other variables. Okay, you guys have heard of independent and dependent variables. In this case we're looking at an independent variable predicting a dependent variable. It's similar to correlations. And remember, we found if two variables were dependent or independent. If they were dependent, we said that they were correlated. This actually does similar things, but we also take it a step further and say, does X predict Y? So basically, does my independent variable predict my dependent variable? Okay, so let's start with the way Excel sets it up is actually a good way to go through this. They start by looking visually at the relationship between two variables. Okay, so I think we talked about this example when we did scatter plots, and that's actually where we're going to start with regression. If you go to add-ins and Megastat, if you go to the correlation regression tab here, you see that they start with a scatter plot and then a correlation matrix and then regression analysis. That's a great way to organize regression. You know, let's look first at the visual relationship. And remember, scatter plots give us strength and direction of the relationship. Okay, so the horizontal axis, or the x-axis, is always going to be our independent variable. That's the variable doing the predicting. Okay, so in this case it's age. We expect age might predict salary. You would never have salary being predicted. You know, you would never try to predict salary, or I'm sorry, you would never try to predict age because people just age every year. So horizontal axis again is our x, or our independent variable, and that's going to be age. Okay, so we can just select that whole column with the label. The vertical axis is always our y-axis, or our dependent variable. What is the thing that we are trying to predict? Okay, and then we'll just put age versus salary. Okay, the rest you can just leave it as is. Click OK, and we see that there is a strong positive relationship between age and salary. As age goes up, salary goes up. And we have some new things here to consider. There's actually our regression equation. This y equals 1.447x plus 8.191 is our regression equation or regression model. We'll talk a little bit more about that when we do the regression analysis, because we'll see it again later. But that and the r squared below it are going to be two of the most important pieces of information here. And we'll talk about r squared later as well. Right now we're just looking at the visual relationship between age and salary. And it's looking good. There's a positive relationship and it's pretty strong. Okay, if we go back to our data, the next step is going to be the correlation matrix. This is similar to when we were finding if two variables were independent or dependent. Right now we just want to see is, does one tend to go up when the other one does? Remember when we talked about, people found a correlation between ice cream sales and crime? Those variables were correlated because they tended to move in the same direction. Now they weren't causal because it's actually just the fact that it's summertime or the temperatures are rising that causes both to go up. Okay, so here, remember, correlations don't necessarily tell you anything about causality or one predicting the other. They just talk about how strongly related the two variables are. And for the input range, we just have to select the two columns. Okay, so this 0.814 is actually our correlation between age and salary. Correlation, or correlation coefficient, as you'll see in the slides, can be any value between -1 and +1. The sign, the negative or positive sign, actually tells us whether it's a positive or negative relationship. Okay? We obviously don't see a negative sign here, so it's a positive relationship, which is what we'd expect. Age and salary move in the same direction. Okay, and remember, positive relationship just means they move in the same direction. Okay, we can still have two things going down, but if they're moving in the same direction, it's still a positive relationship. Okay, so 0.814 is actually a very strong correlation because it's close to 1. Okay, any correlation close to 1 or -1 is going to be strong. So even if I have a negative 0.88, that's, even though it's negative, it's a strong correlation. It's just a strong correlation in the negative direction. Okay, so again, correlation It's going to be represented by R, as you'll see on the slides, and it's between -1 and +1, and it gives strength, basically how big the number, how close to 1 the number is, and direction, the positive or negative sign. Okay, there's mixed feelings about how strong is strong, but for this class we can just say maybe above a 0.5 is a strong correlation. Okay. Okay, so we've visually seen the relationship, and numerically we have a number that shows strength and direction. So we have a scatter plot that shows strength and direction, and we have a number that shows strength and direction. And the slides actually show a couple more examples of different values for different correlations. Okay, our final step in the regression analysis is going to be the actual regression analysis. And Megastat's nice because it's very clear in terms of, what's your independent variable, what's your dependent variable. So let's start with, remember, my independent variable is that thing doing the predicting. Okay, we're not saying anything's predicting it, it's going to be doing the predicting. So it's kind of the one that comes first. So age will be my independent variable, and salary will be my dependent variable. That's the thing I'm trying to predict. And again, you can see how this is useful in business because, imagine I'm Steve Jobs at Apple and I want to know what's going to predict sales of the new iPad. That would be my dependent variable, likelihood to purchase an iPad. My independent variables could be anything from age to income to price points of the iPad. Okay? So this is very useful in business all the time, predicting things like sales, revenue, profits, market share, and things like that. The only other thing we're going to look at is actually, I want you to click on the standardized coefficients, we'll talk about that, as well as the influential residuals. Okay, influential residuals are actually going to show us our outliers. Okay, so we'll see that more in the output. Click OK. Okay, so we have a lot of information here. Just a few things that are going to be really important here. First of all, here's our R that we saw before. Okay? Here's the R squared. We saw that before as well. Remember up on the scatter plot? We saw the R squared. Okay? It's just the same thing, and it literally is the correlation coefficient squared. Okay? But researchers and statisticians actually tend to use R squared more than R. Okay? Because R squared, well, at least in a regression analysis, because the R squared actually tells us, and this is also on the slides, that the amount of variation in Y that is explained by X. Okay, so R squared tells us the amount of variation in Y that is explained by X. So in other words, the amount of variation in salary that is explained by age. Okay, so basically the bigger the number, the better the predictor. The better that your X is at predicting Y. The better that your independent variable is at predicting your dependent variable. Okay? And this is used as a percentage. Okay, so basically we can say here 66.3% of the variation in salary is explained by age. Okay, and I actually want to give you another example. I recently read an article in Psychology Today that talked about nature versus nurture and skills, things like basketball or cello playing. They wanted to see how much is genetics a predictor versus environmental factors a predictor. And they were mainly focused on genetics. Excuse me, and they found that genes actually explain 22 to 36% of the variance in creative achievement. Okay, so basically their R squared was somewhere between 22 to 36%. It probably depended on, what type of skills they were talking about here. So just to quote the article, between 22 and 36% of the differences in creative achievement in the arts and sciences may be explained by natural endowment. In other words, genetics. Okay? What R squared also tells you is that the other, in this case, 88% is being explained by environmental factors. Okay, so for this age salary example, 66% is being explained by age, and the rest is being explained by something else. Okay, that's an interesting thing in itself. Just because we have a low R squared doesn't mean it's not interesting. And we don't expect a really high R squared when we only have one independent variable. I mean, think about it. There's many other things that go into someone's salary other than age. Okay? Okay, so this p-value, we're very familiar with p-values, is actually the p-value for this F test statistic. You don't have to worry about calculating the F, calculating that test statistic. Just think of it as it's a test statistic just like Z score is a test statistic, just like our t-score is a test statistic. And like those, we get a p-value associated with that. Okay, so in this case, our p-value is basically, obviously extremely low. And when the p-value is extremely low, we know we reject the null. But in this case, I haven't told you yet, what is the null in this case? Okay, for regression problems, the null is basically saying that you don't have a good model. Okay, so if you're rejecting the null, you're actually saying you do have a good model fit. Okay, so the assumption is we don't have age doesn't predict salary unless we can prove otherwise. Okay, and that's our alternate hypothesis, that we have a good model, that age is a good predictor of salary. So we're looking for a low p-value. Okay, many times we're looking for that low p-value. And that same exact p-value is down here, which is basically a description of how age as the independent variable is doing at predicting our dependent variable salary. Okay, the final thing, or second to last thing that we're going to talk about on here is these coefficients. Okay, when we develop a regression equation, we actually use an intercept and a slope. Some of you may remember the equation for a line, y equals mx plus b. Okay, using the similar format, we actually create an equation for the regression line. Okay, so this is our intercept, 8.19, and this becomes the slope, which is actually the coefficient for age. Okay, these numbers are what makes up our regression equation. Okay, so we have y equals the slope times x plus our intercept. Okay, y equals the slope times x plus our intercept. Okay, so once we have those coefficients, we can actually create this regression equation ourselves, even if it's not, listed here in the scatter plot. We could have created that equation. And this is the best part of regression. Now that I have this regression model, I can now make predictions, future predictions about salary. Okay, so given this slope 1.447, given this intercept 8.191 that came from my original data, I can now plug in a new age for x to get a predicted salary y. Okay, so that's the best part of it, is doing the predicting. Now that I have this equation, I can plug any value for x to get a predicted y, or basically any value for age to get a predicted salary. The last thing you notice, remember I selected influential residuals. That's basically telling me, okay, where are the outliers and unusuals? In this case, we know that something between 2 and 3 standard deviations is unusual. Something above 3 is an outlier. In this case, we only have one unusual. And I might want to go back to that observation number 8, and just see, basically what's going on there. Cecil. Yeah, she's 60 and makes 122,000. That's significantly higher than the other people in our data set, so that makes sense. You just want to look back at your outliers and say, okay, is this, an error in data entry, or is this legit? And it is in this case. Okay. So that is basically regression in a nutshell. We take a look at the visual relationship. Scatter plot gives us strength and direction. The correlation in the correlation matrix. The R squared, which tells us the amount of variance in our dependent variable that's explained by our independent variable. Whether the model is a good fit, or basically, do we have a good predictor of our dependent variable? And we do in this case because we have a low p-value. And our coefficients, which help us create this equation here, because we have the slope times x plus the intercept, which gives us a predicted y. Okay, so predicted y equals the slope times any value of x plus our intercept. Okay, and that's basically regression in a nutshell. Again, just take a look at the slides, and that'll be a review of what I just did, but now you see it on Excel output.